Welcome, chemistry students. You are welcome to the second semester chemistry course, General and Inorganic Chemistry. Unit 5 of this course is on acids and bases. Chapter 5.4 of this unit is on Pearson's concept, HSAB principle and its importance. The instructor for this chapter is Dr. P. Sharada, Selection Grade Lecturer in Chemistry, St. Joseph's College for Women Autonomous, Visakhapatnam. Learning outcomes. By the end of this chapter, the learner should be able to understand Pearson's hard and soft acid-base theory, classify Lewis acids and bases into hard, soft and borderline acids and bases, apply HSAB concept to account for the stability and reaction preference of chemical species, and also correlate elements position in the periodic table with its hard or soft behavior. Contents. The contents of this chapter are introduction and a recap of Lewis acid-base theory, HSAB principle, properties of hard and soft acids and bases, hard, soft, borderline acids and bases, illustrative examples and some limitations. Now let us recollect what we have learnt in the previous videos on the nature of acids and bases. According to Lewis acid-base theory, electron pair donors are Lewis bases and electron pair acceptors are Lewis acids. And also we have learnt that neutralization is the formation of a coordinate covalent bond between a Lewis base and a Lewis acid. You can see the indicative example here. In this example, you can see nitrogen is having a lone pair of electrons. It is acting as a Lewis base. BF3, boron, is having a vacant orbital. Into the vacant orbital on boron atom, the lone pair on nitrogen is donated so as to form the NH3BF3 compound through the formation of a coordinate covalent bond between nitrogen and boron. So, the Lewis acid-base theory to a very large extent could explain how an acid behaves or what can be called as an acid and what can be called as a base. But there are some limitations to the Lewis acid-base theory. Lewis acid-base theory is only qualitative explanation. Electron pair donor is a base, but it did not tell you why some bases are considered as strong bases and why some others are weak. Simply it said electron pair donors are bases. But why are some bases strong? Why are some others weak? Why ammonium hydroxide is a weak base? So, such explanations could not be given by the Lewis acid-base theory. So, it does not account for the relative strengths of acids and bases, and Lewis acid-base theory also failed to explain the mutual preference of a particular acid to a particular base. While it is very reactive with a particular acid, the same base is not so reactive towards another acid. It is reactive to a particular acid, it is not so reactive to another acid. So, the mutual preference between the acids and bases could not be explained. Also, why are some compounds formed between an acid and a base? Some of them are highly soluble. Some of them are not so soluble. Some of them are very stable. Some of them are not so stable. Such facts could not be explained by the Lewis acid-base theory. So, in order to account for the bonding or the formation of coordinate covalent bond between metals which act as acids and ligands which act as bases, and also in order to account for the mutual preference and also explain the reaction pathway and stability of compounds, the HSAB principle has been proposed. So, the HSAB principle has been proposed in order to address the limitations or shortcomings of the Lewis acid-base theory. See, Lewis acid-base theory only said electron pair acceptors are acids. So, if you have d block elements forming coordinate covalent compounds, the metal is considered to accept a pair of electrons from the ligand. But the same metal has a preference to a particular ligand it likes. It forms a bond very easily with few ligands. It doesn't form bonds with other ligands so easily. Also, the compounds, coordinate covalent compounds, coordination compounds formed, some of them are very stable, some of them are not so stable. So, in order to account for these aspects as to mutual preference, account for the reaction pathway, the stability of compounds, HSAB principle has been proposed. Now, let us see what is HSAB principle. HSAB principle is hard and soft acid base principle which was proposed by Ralph Pearson in 1963. Like binds with like, that is the rule. Like binds with like, or like prefers to bind with the like. Hard acids interact strongly with hard bases and soft acids prefer to interact or interact strongly with soft bases. The HSAB or hard and soft acid base concept is simply this: hard acid prefers hard base, soft acid prefers soft base. Hard acid does not prefer a soft, hard acid does not prefer a soft base, or a hard base does not prefer a soft acid. That is the principle. Hard, hard and soft, soft interactions are strong. Stable compounds are obtained as a result of hard, hard and soft, soft interactions. Their solubility, if the compound is between a hard acid and a hard base, the solubility of the resultant compound is very less. But if the compound is formed between a hard acid and a soft base, or a soft acid and a hard base, such compounds are easily soluble. Hard soft interactions are weaker, they are less stable, and easily soluble compounds are obtained as a result of hard soft or soft hard interactions. Let us see. Let us see the characteristics of hard and soft acids. You can see here hard and soft acids. Hard are high charge density. Hard means they should have high charge density, whether it is positive charge or negative charge. If it is positive charge, you call it as an acid. If it is a negative charge, you call it as a base. But nevertheless, whether it is a hard acid or a hard base, it should have high charge density. How do you get density? Density is mass by volume. So here, how do you get charge density? Charge by the radius of the particular ion. So, charge to radius ratio should be high. High charge density, less polarizable, mostly ionic. They are all hard. What is the meaning of soft? Low charge density. When will the charge density be low? Less charge, more volume, or more radius, big ions with little charge. So, low charge density means more polarizable. Polarization means what? All positive charge going to one side, negative charge going to the opposite side. Polarization means forming poles. What poles? Positive pole and negative pole. So, soft acids and soft bases are polarizable, means because of their big size and low charge, whenever a particular charged species approaches them, they get polarized. That means poles will be formed. A positive pole and a negative pole within the same species will be formed. So, soft means low charge density, more polarizable, and they form mostly covalent compounds. Whereas hard means high charge density, less polarizable, and they form mostly ionic compounds. So what are the differences between hard and soft acids and bases? Hard acid, they have small ionic radius is very small, high positive charge, low electronegativity, and high energy, lowest occupied molecular orbital. That means LUMO. You must have heard in your previous classes LUMO and HOMO. LUMO is lowest unoccupied molecular orbital. HOMO is highest occupied molecular orbital. So they have high energy LUMO. What is a hard base? Hard base also has small radius. It has high electronegativity. This has high electropositivity. This has high electronegativity. It is weakly polarizable. This is also less polarizable. High energy HOMO. So these are the HOMO means highest occupied molecular orbital. So these are the features of hard acid and hard base. What is a soft acid? Soft acid means large. Soft means large. Hard means small. Small, much charge, it will form ionic compounds. Soft means big size, polarizable, it will form covalent compounds. So large ionic radius, low positive charge, intermediate electronegativity, and low energy LUMO, lowest unoccupied molecular orbital. Large radius, intermediate electronegativity, and high polarizability, low energy HOMO. These are the characteristic features of the soft acid and a soft base. So hard acid prefers a hard base, soft acids prefer soft bases is the HSAB principle or the Pearson theory. Why? See, the question could not be answered by Lewis. Why some acids prefer only some bases? Why are you getting compounds which are very stable between some? Why are the compounds formed between some other species are unstable? Stability could not be explained. Preference could not be explained. Solubility could not be explained by Lewis theory. So the same facts are addressed in the Pearson's theory or the HSAB principle. Now this is our periodic table. You can see all the elements that are marked in this orange color are all hard. That is, they have small radius, their ions will have high charge, they are less polarizable, so they form ionic compounds. All those shown in blue, you can see 4D elements, 5D elements towards the end. These are the 4D, these are the 5D. These elements are soft. You can see the yellow ones are intermediate. So 3D series, if you see, the first few elements are hard. The later elements are intermediate. That is to say, they are neither very hard nor very soft. They are intermediate. You can see here these elements are also hard. The yellow ones are intermediate and the blue ones are soft. Now let us see the hard, soft, borderline acids and bases list. You can see here, you can look for yourself. I need not read out. You can see here alkali metal ions, alkaline earth metal ions, aluminium 3 plus, Fe3 plus, Mn2 plus, strontium. You can see here these are all chromium 3 plus, cobalt 3 plus, 3D elements, So these are Mn7 plus, manganese with 7 plus oxidation state, I7 plus, Cl7 plus, all these are hard. Bf3 is hard. But look here, BH3 is soft. BF3 is hard, BH3 is soft. You can see soft means low charge. Here all elements are having 2 plus, 3 plus like that. Of course, alkali metals can have only plus 1, but if you look at the other ions, 2 plus, 3 plus, 4 plus, 5 plus like that. But here you can see the charge is very less, only plus 1, plus, 2 plus, BH3, Hg plus. So soft acids have big dimension, low charge, more polarizable, they form covalent compounds. You can see here hard bases, hard acids, hard bases. Hard bases Bases have to donate electrons. You can always see the base either has an oxygen or a nitrogen. You can see here oxygen, nitrogen, and fluorine. Chlorine is also borderline. Chloride is borderline. Fluoride is hard. So you can see if the donor is an oxygen or a nitrogen or a fluoride, all such bases are hard bases. Or if the donor is an oxygen or a nitrogen or a fluoride, to some extent the chloride, they are all hard bases. If you see here soft bases, you can see sulfur. If the donor is sulfur, it is soft. You can see here I minus, Cn minus, carbon monoxide, all sulfur donors, phosphorus donors, C2H4, C6H6, they are pi donors. So pi electron donors, they are all soft. You can have borderline. You can see here Fe3 plus is hard acid, but Fe2 plus is borderline. You cannot consider it as hard, you cannot consider it as soft. For example, you have chromium 3 plus, Cr3 plus is hard, Cu plus is soft, Cu2 plus is borderline, CO2 plus is borderline. You can see CO3 plus is hard, CO2 plus is borderline. Similarly, BF3 is hard, BBr3 is borderline. Likewise, some commonly listed ligands and metals have been grouped into hard and soft and borderline acids and bases in this particular list. You can bluntly remember that if the ligand has an oxygen donor or a nitrogen donor or a fluoride donor, it is hard. If it is a sulfur donor or phosphorus donor or some pi electron donor like in C2H4 or C6H6, it is soft. Let us see. Now here you can see this is a hard acid nucleus and the electron cloud is so hardly compressed, is compressed, held very tightly. But here you can see the soft thing, this electron cloud is so much expanded, that is it can be polarized. So this is a soft acid or a soft base. This is a hard acid or a hard base. Now hard acid plus hard base, they form ionic compounds. Soft acid plus soft base, they form covalent compounds. Force of attraction between oppositely charged ions is inversely proportional to internuclear distance. So when the size is small, force of attraction will be more. When force of attraction is more, the compound is very stable, it forms ionic compounds. You can see here internuclear distance is inversely proportional to internuclear distance is inversely proportional to force of attraction. Longer the distance, lesser the attraction. So because hard acids and hard bases have small dimensions, attraction will be very high. So they form stable ionic compounds due to high electrostatic attractions and they are less polarizable. Come to the soft side, large size, they are polarizable, they have polarizable d sublevels, there is scope for pi bonding. Whenever d orbitals are available, there is scope for pi bonding. Increase in dispersion energies, because of spreading out, increase in dispersion energies due to polarization in large atoms. London dispersion forces, van der Waals forces, whenever species get polarized, there will be scope for oppositely charged species to get closer. When they get closer, automatically it leads to the stabilization of the system. So polarization in large atoms favor electron cloud expansion of electron cloud and covalent bonding. So soft acids and soft bases form covalent bonds and covalent compounds. Hard acids and hard bases form ionic compounds. So what did we learn? Hard acid plus hard base, compound is ionic. Soft acid and soft base, compound is covalent. Why? Because dispersion or polarizability will lead to expansion of electron cloud and polarization of electron cloud. So oppositely charged clouds will approach one another, the clouds will overlap, leading to covalent bond formation. Now let us see the some typical implications of the hard and soft acid-base theory. Let us see. Relative strength of acidity of hydrogen halides, hydrogen fluoride, hydrogen chloride, hydrogen bromide and hydrogen iodide. So which among them is most acidic? Because hydrogen is hard, H plus is hard, I minus is soft. So the bond between the two is very, very weak. Hard and soft interactions are weak. So immediately hydrogen iodide molecule will break. It will release hydrogen. So acidity or acidic strength is directly proportional to H plus ion concentration. So hydrogen iodide is most acidic, hydrogen fluoride is least acidic. So the relative acidic strength of hydrogen halides can be explained based on the Pearson's HSAB principle. Now let us see another implication is that aluminium and iron. We know, you have ores in the earth crust, metal ores. They exist in the earth crust. Why do we always have aluminium and iron existing as oxide ores? Why not as mostly sulfide ores? It is because Al3 plus and Fe2 plus both are hard. Fe3 plus and Al3 plus both are hard. Because they are hard, they will prefer a hard base. They are hard metals, hard acids. Al3 plus, Fe3 plus are hard acids. Because they are hard acids, they will prefer a hard base. What is the hard base here? Oxide ion, O2 minus is the hard base. So that is the reason why in the earth crust you will generally find aluminium and iron ores as their oxides. But if you look at mercury and silver are soft. Just now we have seen Hg2 plus and Ag plus are soft. Sulfur or sulfide is a soft base. Sulfide is a soft base. Mercury and silver are soft acids. So these metals, they exist in the earth crust as their sulfide ores. Aluminium, iron exist as oxide ores. Mercury and silver exist as the sulfide ores. Now let us see the next example. Hydrogen bonding with oxygen, fluorine and nitrogen only. Whenever we discuss about hydrogen bonding, we will say only oxygen, fluorine and nitrogen. Why? Because oxygen, fluorine and nitrogen are, I just now told, they are hard. H plus or hydrogen is also hard. So hydrogen bonding is always seen only with these three, not with others. Why? Because others are soft. Okay. Next, see another implication. Another implication is that mercuric hydroxide is soluble in acidified aqueous solution. Mercuric hydroxide. Why mercury is soft? O is hard. OH low O is hard. So when you put a drop of acid, H plus you are providing. That means you are providing a hard ion. Immediately OH will say sorry to mercury and it will go with hydrogen. So mercuric hydroxide, if you put a drop of acid, it will become soluble in aqueous solution. But if you try to dissolve mercuric sulfide by putting one drop of acid, it is insoluble. If you try to dissolve mercuric sulfide with one drop of acid, it is insoluble. But the same thing, you can dissolve mercuric hydroxide by putting one drop of acid. Why? Because here oxygen is hard. It will immediately break the bond with mercury and go with hydrogen, H plus. Whereas here it is sulfide. Sulfide is soft. It will nicely bind with mercury. It will not leave mercury even if you put a drop of acid. Silver iodide is water insoluble, but lithium iodide is water soluble. Silver iodide means silver iodide is water insoluble. Means what? Silver iodide is very, very, very stable. Lithium iodide is water soluble, means what? Lithium is hard, iodide is soft. So the bond between them is very weak and hence it will easily dissolve in water. But if you try to do the same thing with silver iodide will not dissolve in water. So now let us see the limitations of the HSAB principle. Just like Lewis acid base theory, though it could account for the stability, though it could account for the mutual preference, this particular theory is also qualitative. It is not telling why some are very strongly acidic, why are some weakly acidic, or why some are strongly basic, why some others are weakly basic. This theory could not explain. It is saying this one prefers this. It is saying this is strong, this is weak. But why the strong one is strong, or why the weak one is weak, or why the question to why or how much is not answered by the HSAB principle. Soft base SO3 2 minus can displace hard base fluoride. You can see this reaction here. What is the reaction? Sulfite plus hydrogen fluoride is giving the bisulfite plus fluoride. That is, fluoride is getting displaced by SO3 minus. How come? SO3 minus, sulfur is soft. How can it displace fluoride which is hard? Hydrogen is hard, fluoride is hard. But still the soft one is able to replace fluoride and take its place. So this could not be accounted by the HSAB principle. Direct contradiction of Fajan's rules. See, the HSAB principle is also a direct contradiction of the Fajan's rule, which means whatever Fajan has proposed, the same thing is contradicted here. We are saying it is soft, we are saying it is hard, but according to Fajan's rule, we have some other definition. So this is a direct contradiction of the Fajan's rule. Then of course solubility of H2. You can see here, see, H plus is hard acid, H minus is soft base. Together they form H2, but it is covalent in nature. See, you can see here hydrogen molecule is covalent in nature. It is quite stable, but this could not be, stability of hydrogen could not be explained by the HSAB principle. So with this we come to the close of this entire paper. We come to the last part, and let us recollect what we have learnt in this last part of this entire paper, or the last chapter of the 5th unit. So we have learnt that HSAB principle says like prefers like, hard prefers hard, soft prefers soft. Then we have also learnt that less polarizable, high charge density species are hard and they are ionic in nature. They form ionic compounds with other hard bases or acids. The more polarizable, low charge density species are soft and they are covalent in nature. That is, through the overlapping of electron clouds, they prefer to form bonds. We have also learnt about some applications of HSAB principle along with some other limitations. So in this chapter we have learnt about the principle, we have learnt about the explanation for hard and soft acids and bases. We have seen the list, then we have seen some applications, and we also understood some limitations of the Pearson theory. With this we close this chapter as well as the paper. Thank you. All the images are adopted from open pages in public domain. Thank you.